Good afternoon, everyone. I hope you are doing all right. In our area, it's stormy a little bit, and I can hear thunder. Oh, let me get my microphone. So it's a kind of thunder going on in our area. If you hear loud sound, and that means it's a thunder, nothing that I'm producing that sound, okay? Okay. So we are coming towards the end of semester and coming towards the end of the let's say the content I'm planning to introduce to this class. So last class we talked briefly about quantum nature of light, and that is the beginning of quantum mechanics. Okay, and just like I said, quantum mechanics can be taken for several semesters, and that was just one class. And similarly, today it is called atomic physics, uh, and this can be also, a semester course. But again, we are just doing in one class. The main reason I'm doing, going through this, usually, what happens is the instructors basically stops after the interference and diffraction, then they don't move forward. I mean, they just cover up to that point. But turns out in the MCAT, they ask questions from all these, including the nuclear physics. So I'm just trying to, like let's say, give basic idea of these things so that if you are planning to prepare for MCAT, you can actually, have seen those materials. Okay, it's not going to be totally new. So that's why I, talked about sound. Usually the sound is done in, it should be in physics one class, but I included a little bit because we are talking about waves, and starting from there kind of made sense. And also that is also included in MCAT thingy. So I wanted to do that. The only thing that's mostly going to be missing going to be the thermodynamics part. Other than that, I think whatever we did in physics 1 and physics 2, that should cover the whole materials. That's for the MCAT. And of course, these are also called modern physics, kind of gives us, that idea of not just the classical physics that developed before, let's say, 20th century, but it is modern physics is like it developed in 20th century. Okay, so now when we let's see, yeah, I think in physics 1 when we talked about a little bit about the so what was that topics that we included, for example, Avogadro's number, okay, where we use that to estimate the mass of the object, and but it was in terms of moles or number of molecules in a mole, right? So we had this Avogadro's number. So the Avogadro's number basically assumes that the atom is the smallest unit of matter. So you keep breaking matter into smaller and smaller pieces, and by the time you get there to the atomic level, then you cannot break it apart anymore. That's what it assumes. Okay. So what's inside the atoms? Once this see here, this experiment. that I have listed here basically discovered what's called cathode rays at that time. Turns out those were electrons, okay? So the electrons were discovered at that time. So there were electrons coming out of the atom that, at that time thought was the smallest unit, cannot be broken, right? So now these electrons are coming out. Oh, so that means it's not no more, breakable anymore. So that means, okay, how the atom is made. So that curiosity basically, went into the development of atomic physics. So how did the structure of atom was actually, like let's say, how do we settle on the structure of atoms? Okay, what was the process? What went in that process? That's what we're going to be talking here in this class. Okay, so discovery of the electron led that, okay, there are negatively charged particle, but there was, the at that time we already knew atoms were neutral. Means if negative charge coming out, that means there must be, they must be leaving positive charge inside, so that, altogether they were neutral. So because of that, this discovery of electron, they came up with this idea of the atomic model, also known as plum pudding model. Okay, so for me it looks like a cookie. Okay, like a chocolate uh, cookie, or you are putting some M&M on that. My kids used to like that. So anyway, so that's what it looks like. So there is a dough of positive charge, that's what they said. Okay, and electrons are embedded. Okay, so it's like a plum on the pudding. So that was the model. So if we visualize that bit more elegantly, now we see something like this. So these dots represents the electrons, and they are spread all over this dough, and dough is made up of positive charge. Okay, so Z here is called atomic number. We'll talk a bit more about it in next class when we talk about nuclear physics. Okay, but of course the atomic number, now, in periodic table they have this atomic number. That means it has that many protons or the electrons. So that is the fully developed model for now, right? So that's what we are showing right now, but it was basically something like this. Okay, so it's called plum pudding model. Okay, so given by J.J. Thomson. Okay, great. So there are electrons, but some electrons can just get out from there, and you can detect them. Okay, and that's what Thomson thought, he discovered. So now, then comes the another experiment. See the timeline here. It was 1897, and it is 1911, so 14 years. After 14 years, okay, the Rutherford was doing this what's called gold foil experiment. So gold, because you can, make it very thin strand out of gold. Okay. So at that time, the plum pudding model was something like this. So that means, what do we expect when we have this thin film of gold, it has several atoms. So that means there are these negative charges, and then there is whole lot of positive charge, dou of positive charge, right? So that's what expected. So the expectation. So now what Rutherford does is fire some alpha particle. Basically, alpha particles are helium atoms. Remember, helium has two protons and two neutrons and two electrons orbiting around based on what we know now, okay? Two protons, two neutrons, and then electrons orbiting around. So if this electron gets out from there somehow, the leftover gonna be this proton, proton, neutron, neutron, and that's what called alpha particle. So you can have this radioactive material that can suit this uh, helium atoms basically. So it has positive charge in it. Okay. So now you are like firing bullets on a paper, for example, right? You are firing bullets on paper because it's kind of heavy. It has proton and neutron, so it is heavy. So it's like a bullet going on paper. And then the expectation was that, they're going to be, see, when you have this positive charge everywhere, so if you see the positive charge here, here, everywhere, that means you expect there's so many of these alpha particle to be bouncing back and going all over, and some of they may, penetrate and go something like that. So that's the expectation based on plum pudding model. But the experiment shows something like this that I have sketched here in this diagram. Okay, so most of these rays or alpha particle, they pass something like this, mostly straight. Okay, and some of them is scattered, something like this. Very few of them. Okay, so what's going on? So if the positive charge was everywhere, then a lot of them should be scattering, coming back, because positive charge repels the positive charge, right? But what happened here is that only few of them are coming on this side of the screen, but most of them just go and make a big bright spot there, down there. Okay, so that was a dilemma. So that means this model given by Thomson, this plum pudding model must not be correct. It is not correct because the positive charges are not everywhere. Okay, so now to explain, had to come with the new model where all the positive charges were put at the center of the atom, okay, and electrons just orbiting around, just like sun is at the center of our planetary system, right? So planets orbit around and sun is at the center. So that's why the name planetary model, okay? So electrons are like planets that's orbiting the positive charge, and so that means there is a lot of empty space in between electrons and the proton. So that's why only the one that directly came close to that got scattered. All those missed, they just went straight. Okay, so that's how the planetary model explained this scattered light, or I should say alpha particles. Okay, great. But there was a problem, a couple of problems with this planetary model. It wasn't explaining certain thing that what the physics, thought it should. So for example, unlike planets, they don't have charge, and because of that, they are not releasing any energy. But electrons, they are charged. So the classical theory, for example, what happens when electron oscillate? So for example, in planetary model, electron is going back and forth around the, let's say, central positive charge. And from the experiment, it was known that when electron oscillate, for example, in our antenna, we talked about antenna when we talked about electromagnetic wave, what happens? They release this electromagnetic wave. When they release electromagnetic wave, so that means electromagnetic wave has its own energy, right? And so that means the atom is losing, or the electron is losing energy. If something is losing energy and going around, then what happens is eventually it spirals down. So this is the prediction of the Maxwell's equations or classical theory. Okay, that was one problem. So that means it should give us some sort of spectrum with, at the beginning, it is moving past. Maybe it's emitting higher energy at the beginning, and then lower energy decreases. And we know high energy, if we look at the visible light, the blue light has higher energy, and then red light has a lower energy because we now know, even from the last class, and that blue has the largest frequency among the visible, colors, and the red has the smallest frequency. If we talk in terms of wavelength, then it becomes opposite though, right? Because frequency and wavelength, they are inversely related, so then don't get confused. So here I'm talking in terms of frequency because we wrote energy was h times f in particle model, right? Photons. So so that means at the beginning, when it is moving faster, it is more energetic. It emits more energetic. So maybe we expect blue, and then slowly transition to the other color, eventually to the red. Okay, so that's what we expected. But when experiment was done to obtain the spectrum, this is what we got. So we thought, okay, this planetary model predicted this kind of a spectrum where it gradually transitions and gives the all colors. But actual spectrum, this is a spectrum from hydrogen atom. It shows there are lines like red color, yellow color. So that means it's not emitting energy all the time. Okay. It's not, spiraling down and emitting energy all the time. Another problem, once it is spiral, see there is negative charge and there is positive charge. So that means it should just go and combine with the positive charge and the atom should collapse, right? So if the electrons are not there, so for example, if planets are not there, if they all go and fall in the sun, what's going to happen? And that means that's the collapse of solar system, right? Same idea. If the electrons go and collapse on the or combine with the or interest to the let's say positive charge and becomes neutral, so that means the atom, this this does not exist. Planetary model does not exist. Planetary model collapses. Okay, so that's the problem. So two problems. Of course, the atoms not collapse, they exist, right? So all the matters are made up of atoms. So that cannot be true. So it cannot be emitting energy all the time like this. Okay. And even when, if it was emitting, it's supposed to emit something like that, but it's emitting this line spectrum, what we call. Okay. So this observation of line spectrum and existence of atom themselves kind of raises question on this planetary model of the atom. Okay, so that is about the planetary model. And I have a question for you. It's a bit longer to read. I did not write question myself, this one. I was a bit being lazy here. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what happened here. So mostly C. Yes, it assumes the electrons is stationary around, and that is the violation of classical electromagnetic theory. So yes, C seems to be better. Okay, just like you cannot put small pieces of magnet on the metal, near the metal. What happens? They go and collapse. All these are gonna be sticking on the magnet. Okay. So so to describe, why the spectra is there, what happened in Rydberg basically, did not derive this equation, but by looking at and measuring the values, he put together this equation. So this equation basically describes why we get this kind of line, okay? And came up with this constant. And what is that constant? That constant needed to match these values, okay, for the hydrogen. So he did partial work here, okay, to explain that. So this equation explained those lines and gave the wavelength of this line. So for example, here red you see it is slightly more than 650, and these are in nanometers, by the way. Looks like unit is not there. For the hydrogen, the red light coming from the hydrogen atom has a wavelength slightly larger than 650. And similarly, there was these other colors. Okay, looks like yellow is not there. So that is good, but in physics, what we want is, okay, where did this equation come from? You cannot just put together something and say, okay, there you go. We need that coming from some basic principles and put together using valid math and have that equation. Okay, so that's what we want in physics, not just an equation. This kind of equation is called empirical equation. Okay, so if experiment supports the equation, then say, okay, it works. Okay, but we also want to know, okay, where it's coming from, what is it? Okay, where did you get it from? And so on. That kind of question we like to ask. And there was no answer for those questions. So there were others basically searching for that kind of answer. Okay, so that's where the Bohr comes in the uh, let's say enters the scene, comes to the scene, and then solves or the explains this problem by making very bold move. Okay, so that's what we're going to be talking about. But let's wrap this up with this question before we move to the another model. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C, and that is correct answer. Okay, so basically positively charged particle passing through thin sheet of gold in that case, right? But here it says newly discovered element mostly goes straight through, but a few particles are deflected. So basically it is Rutherford nuclear model. Okay, so now let's move to Bohr's atomic model. So Bohr basically used this idea from quantum mechanics packet of energy, okay, photons. And then, in the planetary model, and was able to explain it. Okay, so so basically gave answer of most of the question we had for atoms that has just one electrons orbiting in the outermost shell. Okay, so that means all the atoms or the elements that are on the first column of the periodic table. Okay, so for example, hydrogen here, helium, I think beryllium, and so on. Most of the metal, they are in the first and second column of the periodic table. Okay, so that kind of material. When there are more than one electron, what happens? Things get complicated, but later the same idea was expanded and was able to, predict all the spectrum you can see, not just from hydrogen, but from the other atoms as well. So that is a bit complicated, but basic principle base is the Bohr's model. So that's why it is kind of very important to understand science, or even most importantly, to understand the atoms. Okay. So because of these knowledge, the lasers were discovered, and these days lasers are used everywhere, right? So problem with the planetary model was that it was moving, and because of that, classical theory says, okay, it uh, basically emits the energy and then eventually collapse. So we needed to keep them in place, right? We needed to keep them in place. So Bohr says, okay, they are there, so they are not emitting energy unless, when, as long as they are in that particular orbit, in a particular orbit, they don't emit energy. And those orbits are called stationary orbit, and that state of the electron is called stationary state. And that means one electron can be in one of the stationary state, or another stationary state, or yet another stationary state. So all these are for same electron according to Bohr's atomic model. Okay, so they can be at different energy levels. So most of the time they spend what call ground state, closest one near the nucleus, positive charge. But other times they may, if they get excited somehow, if we let's say shine some sort of light, energetic light wave, I should say, then they may jump there, may even jump there. So in that process, they are absorbing the energy, and when they jump back, they don't stay, like long time on these orbits. So when they jump, they come back here. When they do, they emit the what we call photon. Okay, so they emit the light, and those appears as a spectrum. So that's why there is only certain wavelength rather than all possible wavelength predicted by planetary model. Okay, so these energy level, these orbits were discretized. So he used this idea of discrete energy to come up with this model. Okay, so since a charge is moving around another charge, there are going to be force between them that we call electric force, given by Coulomb's law, right? F is K Q1 Q2 over R square, and there is attracting force, just like planet gets attracted by the sun's gravity, and then since it is moving, it just keep going around. Okay, kind of similar idea here. So he used that, as long as electron is not jumping from one state to another state, as long as it is staying on that particular state, it follows the circular motion equation given by Newton's second law. Okay, so net force in this case is the force between proton and electron. Okay, and r is distance between them, and of course we know K, Coulomb's constant. Okay, so that's what I'm writing here, force between these. And mass times acceleration for radial orbit is v square over r. And you may see there is n subscript here on the r, because r can be, for example, this can be r1, and some other time the electron, same electron, maybe on this orbit, maybe we want to say r2 and r3 and so on. Okay, so that's why if it is in this orbit, then we have to write r3 here. If, or when it is at this orbit, then we have to write 2, 2. When it is at here, then 0th, and so on. So rather than, we don't know where it is, so we say, okay, wherever it is on the nth level of that orbit, and we write the subscript for that. Okay. Okay, so now looks like there is Rn here and Rn is squared, so we can cancel that. And this is k times e squared. And remember, both of the charges, their value of a positive charge is E, value of negative charge is also E. And if there are, Z number, so depending on how many of they are there, it is just the equation that drives the, let's say, the force between one proton and one electron that going around that positive charge. So that's what it is writing. So in this case, this mass would be mass of electron. Okay, mass of electron. So we can write something like this. See here, mv square. So I'm writing this way, so that this looks like a kinetic energy as well. So whenever we need kinetic energy, remember, kinetic energy is half mv squared. So the kinetic energy of an electron is Ke squared over 2 times Rn. So that is the kinetic energy of an electron. So we're going to be using this equation later. Okay. Okay, so basically this helps in this model, this helps to give the radius of the orbit and tells us where this electron is, in what orbit the electron is in. Okay, so that's that. Now, since the spectrum were visible, there were spectrum, line spectrum, remember? So that means there are this light, light can come from the atom, and atom still survive. How does that happen? So that explanation was needed. So he already discretized the orbit, and then now he says, okay, when it emits the photon, what happens is when it jumps, it emits the photon. So for example, it was there and it now jumped there by emitting photon. So it had higher energy when it is, at higher level. And when it comes down to lower level, what happens? Now when it starts orbiting around, now it has new energy and it emits energy in the packet, in the form of packet. of energy, which we call photon. Okay, and photon we know has energy h times f, and f, so different frequency gives the different color. So the color you see in the spectrum line is the result. For example, if it is high energy, that means higher frequency. So that means the color gonna go in the blue side if it is invisible, or even could be in ultraviolet. Okay, depending on what the gap of this is. Okay, so it is at this level, it is that level. So it's like saying, okay, a gravitational potential energy here when you are at 10 meter versus when you are at 8 meter. So larger the gap, larger gonna be energy here, right? Because it's gonna be mg times, let's say h, change in height. So larger the gap means larger the height, means larger the gravitational potential energy change. Similar idea, but this is not gravitational potential energy. It is basically this, the energy comes as light, and this light can have color, frequency, wavelength, and so on. Okay, so that's what it says. So there can be absorption, there can be emission. So if it absorbs, so if you are shining light, it's going to absorb a certain frequency light, okay, and then it can it absorbs only certain frequency light, the enough to get to another level. If the energy that you are supplying to this electron right now here, and if that's not sufficient to go there, it's not going to jump at all. It's not going to take it as at all. Just like in photoelectric effect, what happens? If the energy of the photon is not enough, then electrons not gonna absorb the energy, right? So that's how we explain the photoelectric effect. Einstein explained the photoelectric effect. So basically the same idea later Bohr is using to explain, okay, when and how much energy is emitted. And that emitted energy has a particular wavelength, and spectrum is the display of wavelength and frequency, or just wavelength or just frequency. Okay, so that's what the spectrum is. So that's what the Bohr used. Okay, now which orbits are permitted then, right? So why it can have just a particular orbit, why it cannot have in between orbit, for example, right? To explain that, Bohr used this idea of standing waves. Remember, a standing wave in a string or uh, in a pipe, what happens? We don't get all frequency there. We get integer multiple of the base frequency, fundamental frequency. So that's what we learn. And Bohr used that idea here. See how the idea from one discipline, another topic, and so on, is being combined to get or explain certain things by getting new equation. So that's how physics is done in theory. Theoretical physics is, that's how it is done, right? In experiment, you set up experiment, but in theory, you have to try to, get this different idea from different field and put them together to see if it using correct mathematics, of course, and all level of mathematics you need to know, and then by doing all those, see if you can come up with the new equation. Okay, so here Bohr is doing this, and this also explains the process of development of physics. So that's why I kind of like it. Okay, so just like this, if this is, for example, 10 hertz, let's say this F1 is 10 hertz, then we can have only 20 hertz here and 30 hertz here, no in between. So that's what this the classical experiment shows us. So what Bohr does is says, okay, only those stationary orbit. So frequency and certain multiple of those frequencies, they can, like let's say, not in terms of frequency, but in terms of radius, for example. It can have only that, and that is integer multiple of wavelength of the wave. So 2 pi r is the circumference, right? So in one circumference, there has to be either one wavelength or two wavelength, three wavelength. We cannot have 1.5 wavelength or 2.5 wavelength or 2.25 wavelength and so on. So that's what Bohr is saying and introduces this equation. So from this, you can calculate the radius of nth orbit, okay, if you know the wavelength. And these are quantized as well. And like, so that means since they are moving around, they have angular momentum, right? So we learn that angular momentum L is R times P, or let's say if we were to ignore this cross multiplication, we can say, okay, R times M and B, P is P. So that means you can have only quantized angular momentum. So that means a certain orbit here, Rn. And now here, you see this wavelength. For the wavelength, he is using this idea of matter wave. See, this is electron, right? We're talking about electrons orbiting. So if you use that as a particle, then you don't have wavelength there. So since it was already, known that matter can have wavelength, we talked about this in last class, right? De Broglie wavelength, right? So that's the equation he is using here, okay? H over mb, and this is momentum here. So now what happens is we can figure out radius of the orbit. The radius of the orbit depends on mass. Of course, the electron has a fixed mass, so we don't have to worry about it. It's a constant for an electron. Now it depends on speed and which orbit it is in, and h is also constant. Okay, h is also constant. So since we know Rn, so we can use this Rn in that equation and write the angular momentum. Okay, so that's what it is being done here. And there is this notation for h over 2 pi. It's a kind of standard notation. It's called, see how rather than h, there is this bar, h bar. It's also known as h bar, but it is basically h over 2 pi. So I'm writing h bar there, uh, just in case if you see somewhere in the book and if you get confused. But I'll be mostly using just h over 2 pi. Okay. So we have this Rn and we have the angular momentum. After quantizing the orbit, you have this relationship here. Now this h is a Planck constant, and remember that goes to the hf thingy over there, right? So now classical theory and quantum theory are being fused together. Okay, so remember we had this equation for mv square using Newton's second law, And now we have this equation for Rn, and actually this can also be written as let's see. So if you plug that in there, this MB cancels, giving you just this. So now you have NH cross, H bar, sometimes H cross, that's what it is called. So we are in the process of deriving this different energy levels for an electron that's going around atom, okay? And that was derived by Bohr to explain the, to further the atomic model from the planetary model, right? So in that case, he used this idea from classical physics and quantum physics. So let's take a pause here before we keep going. So here is a question. So circumference C of a ground state orbit of the electron in hydrogen and this wavelength are related. So how did the Bohr use that idea? Okay, so what do you remember? Go ahead. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. We got mostly A and C. So what did we see in the previous slide? It was 2 pi Rn is n times lambda. So that was the idea. And this whole thing is circumference, isn't it? So if we're talking about ground state orbit, then we can say n is 1. So in that case, we can just write c is equal to lambda for n is equal to 1. So yes, this kind of looks close, but remember that this is basically, if this was r, that would have been the circumference. So it looks like A is the best choice here. And there is another question. So let me start the poll. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C, and that is correct because we have circumference is n times lambda. So for n is equal to 1, it's C is lambda. For n is equal to 4, C is going to be 4 lambda. So 4 times larger, right? So yes, so C is correct answer. So now this was a little break to understand, like if we got that, the quantum nature, how the standing wave was introduced in the atomic model for the electrons they were orbiting around, right? So now we're going to keep continuing the writing the equation for the energy. And remember, energy means kinetic energy. So electron has a mass, so that means it has a kinetic energy, and that is given by half mv square. And we need potential energy, and potential energy is electric potential energy. So we're going to use those two and combine. Okay, so to write the equation, so looks like it's a good time to take a break. So let's take a break, and after we come back from break, we're gonna basically derive that equation. Okay, that gives the all the line spectrum and so on. Okay, so I'll see you in 5 minutes. Okay, folks, welcome back. So this equation, this was the very first equation in this model we derived by using Newton's second law for circular motion of electron around a proton. Okay, and now we want to rewrite this slightly differently so that we can introduce that H prime thingy. So going from here to here, I haven't done anything new. Rather, I'm just multiplying by this and dividing by this. Okay, so what's the reason? Because if I do that, then it becomes m square and r square and b square, right? So it's like saying mrb squared, and this mbr or mrb is the angular momentum. So we want to write this in terms of the angular momentum. And remember, the angular momentum was quantized something like this, or an h over 2 pi. So we can replace this with this one here, but this is being squared. We're going to write something like this. So it is written like h bar squared. Okay. So that way we can write kinetic energy and potential energy in terms of something like this. So that gives us the nth value of Rn, nth value of the orbit. So by, rearranging this equation, one of the R cancels, and solving for this Rn over here, we get this. And this is written as n square times a0. So this a0 is the radius of the very first orbit. It's notation for the radius of the ground state. Okay, so that a0 in this case is everything but n square because we are writing n. So when n is equal to 1, radius of the orbit is exactly equal to a0. And when we plug in the value of this h bar, so that means h over 2 pi m and this k and charge of an electron and so on. So we know all of these are constants. So when we do that, we get this. So this is PM means picometer. So 1 picometer is 10 to the power negative 12 meter. Remember, nanometer is 10 to the power negative 9 meter. So if you have a nanometer and if you divide that into 1,000 parts and pick one, and then that becomes the picometer. Thousandth of a nanometer is a picometer, even smaller. Sometimes this is also written in terms of what's called angstrom. Okay, so 1 angstrom, and angstrom is denoted by a round circle on top of A. That's kind of weird notation. Is 10 to the power negative 10 to the power negative 10, something like that, meter angstrom. So it is not in the nano pico, but it's in between nano and pico. Just a tenth of a nanometer is a angstrom. So here this is pico 10 to the power negative 12, and this is angstrom, that is 10 to the power negative 10. So when I write this in picometer, or let's say in meter, it's going to be 52.9 10 to the power negative 12. But I can also write this as a 0.529 10 to the power negative 10. So I moved these decimal to two places here. So this became 10 to the power negative 10. So that is kind of easy to remember, around half angstrom. Okay, around half angstrom. So that is the ground state. So that is also the size of a hydrogen atom. So how big is the hydrogen atom? The radius of hydrogen is half angstrom. So diameter going to be double of that. So 1 angstrom, around 1 angstrom. So atomic size is 1 angstrom. And of course, once we go, the uh, higher, let's say, atomic number elements, then their size is going to be a bit bigger. But if someone asks you, like, what's the size of an atom? You can say, okay, it is in the order of 1 angstrom. So was able to actually see the nanometer. So I guess I showed you this scale here, how long a meter is, and thousand of that is a millimeter, thousandth. So it goes from this long scale to millimeter when we divide that into 1,000 parts. But to go from meter to nanometer, you have to go through that, 3 times of that thousandth part. Thousandth of a millimeter is micrometer, and thousandth of a micrometer is a nanometer, and tenth of that nanometer is 1 angstrom. So you can imagine how small these atoms are. And with this theory, he was able to actually calculate the size, tell how big they are. And turns out these days we have electron microscopes. And of course, electron microscopes cannot see electrons, but instead of light, they use electrons. And they have very high resolution because electron wavelength is very small. And because of that, what happens is now we can actually see the tentative size of atoms. Although we cannot see electrons, we can see the atom. Okay, so we can measure that way, and turns out this theory is right. That's the size of atom. Okay, look at the beauty here. So you just use some of the theory from physics, combine them together, and now you can tell how big an atom is. Okay, and not just that. Now with the radius known, you can also write kinetic energy, potential energy, and add them together and write the how much total energy gonna be here in the ground state or first excited state, second excited state, and so on. Okay. So energy of any particular state. So nth state is potential energy at that state and kinetic energy at that state. Okay. So now potential energy is, remember, potential energy, U is force per unit charge, and we wrote that as a K Q1 Q2 over R. So that's why you have 1K and then E, charge of an electron, and then charge of proton, I should say, it's a positive, and this negative is charge of an electron. Remember, uh, potential energy is scalar quantity, so we need to use the sign of the charge as well. Okay, plus kinetic energy, so half mv square, we already know mv square is this much, means this much. So half mv square going to be just this thing with 2 in the denominator. So we can write that. So basically, those are the things we are using here. Okay. So we can replace this Rn by this, and that way all the equations. So this Rn and this Rn. So we can eliminate that with just this most of the constant and the n. Okay. So when we do that, what we get is this. So now all these are constants. And only thing that is not constant is n square. Now the n square is in denominator. Okay, so that's that. So all these constants except the n square, including the negative sign, is called E1, and that is the potential energy, that is the energy of, total energy of an electron when it is at ground state. Okay, and it turns out that when we plug in all these numbers and calculate, we get this much in terms of electron volt. Remember, one electron volt is a very small unit of energy. In terms of joule, it becomes 10 to the power negative 19 joule, just like charge of an electron. So with these numbers plugged in, and then with this conversion from joule to electron volt, we get this number, and negative sign is already there, and that's the ground state energy of hydrogen atom. So now we know how far the electron is from the proton, or let's say nucleus, in a hydrogen atom, and what's the energy. So now, see, if it has energy E1, then this one, the second one, gonna have E1 over n square, and n means 2 for the second, so that means it's gonna be E1 over 2 squared, means 4. So only the energy level going from first to second, only the quarter energy is available. But remember, this is negative, so smaller negative number means larger value. So energy is getting higher and higher because these are negative. So number getting smaller means getting smaller. Sorry, larger. Okay. Number is smaller, smaller negative numbers means they are larger, basically. So this is called ground state, first one, and then one bigger than that is called excited state. So electrons mostly spend time on this ground state, but if somehow they get pushed from that orbit, they may take this or that or higher depending on how much energy being used to push it with. Okay, and then they spend about microsecond, and then it starts coming down. Okay, so when they are coming down, that's when they emit this spectrum. And turns out when we calculate the wavelength for these, that matches with the wavelength that we, experimentally observed spectrum. So this whole thing works out really good. So Bohr explains this spectrum observed and even gives more, for example, what's the size of hydrogen atom and so on. Big work, groundbreaking in terms of, understanding of how the atoms are, how atom behave, the atomic property. Okay. So now with that, I have a question for you. So Bohr radius means that A0 we talked about. Okay. So A0 was the very first one. Of course, there are others as well. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So we got most of them except E, and there are more for D, and that is correct. I think our equation is this. So for third one, since there is n square dependent, what happens? So if you go 3, it is 9 times. Just like energy was 1/9, radius is 9 times more. So what it is saying is, let's say there is a nucleus and then first orbit is here. Let's say this is 1, it is half, we know in angstrom, but let's say 1. Then second gonna be n square times 1 means this being 2, n is equal to 2 means it is 4 times A0, and third one is 9 times A0 and so on. Okay, so that's how it increases. So that means once we go the higher the orbits are, they are separated more and more. So to go to higher orbit, it needs a lot of energy. Okay, more and more energy. So that's what it is showing. Okay, now in terms of energy, so if we were to put energy levels, for example, what happens? We have, looks like I cropped the ground state here. So we have negative 13.6. And the other one gonna be negative 13.6 divided by n square, means when n is equal to 2, this becomes negative 13.6 divided by 4. So that means 4 times 3 is 12, and that's what that number is. Okay, so you dividing this 13.6, negative 13.6 by 4, you get this. You divide this by 9 for n is equal to 3, you get this, and so on. So you now know the energy of all these orbits on the ground state and all the excited one. Okay, and rather than drawing in circle, they are drawn as a straight line to visualize. Okay, so that's what you see. Now what happens? Let's suppose somehow the electron that is on the ground state gets energy somehow. You shine light laser, let's say you hit that with the laser, it absorbs the energy and then jumps. Depending on what color laser you are hitting with, or what electromagnetic wave you are hitting this with, what's going to happen? It may jump in one of those. Okay, and let's say it kinda first it absorbs and goes somewhere there. Let's keep things a bit simpler. Then remember, on the higher state, it spends only about microseconds, and after that it starts coming down. So for example, when it comes from here to here, one possibility is that, right? Or it may just jump back down here. That's another possibility. So in that case, how much energy is being emitted here when it jumps from this higher state to this one? That is given by this equation. So whatever the final is here, and initial is this, right? So initial here, if it's jumping from E3, so that means it's E3 minus E2. Now, if it is jumping from E3 to ground state, then this delta E gonna be, so this is when jumps from n is equal to 3 to n is equal to 1, not 1, 2, that was for 2. Now, when jumps from, let's say, n is equal to 3 to all the way to n is equal to 1, so these are different possibilities, okay? And so it's jumping around. So in that case, what happens? This delta E, or the energy emitted, going to be E1 minus E3. Final minus initial, remember. Okay? So that's how it works out. Okay? So that means all you have to do is take the difference between these two to figure out the energy difference there. So final minus initial. So for example, negative 3.40 minus 1.50, right? So that difference is the energy difference. Now, that energy difference, so if you want to calculate what wavelength is coming out, then you can use that as h times For frequency f, for wavelength, it is c over wavelength. So now, if once you know this energy difference, you can calculate the wavelength for that jump. And once you know the wavelength, you know the color. So for example, we have light bulb. How light bulbs emit the energy? Basically, this is what happening. So you supply electricity, it becomes excited, we say. Okay, it absorbs the energy and it gets excited, goes to a higher level and comes down. So there are several electrons, billions of electrons. That's exciting at once, okay? Because there are billions of atoms there. So billions of electrons exciting and going higher and coming down. So in that process, they are emitting light. And some of them may be emitting, one color, others emitting another color, and so on. All the light that we can see results from the jumping of the electron from third or let's say higher state to this one here, second one. Okay, all the higher to second. Okay, the one that jumps from third to second has the lowest energy, so that means it's going to have longest wavelength, so that's why it is red color. And the one that jumps from fourth to the second, this produces blue color and so on. Okay, so these different color are originated from this jump, these different colors. And when you do the calculation and figure out the wavelength, it turns out, okay, you get those colors. Isn't that nice? And there is this big gap here. When it goes all the way down here in the ground state, that's when it emits the most energetic, and those going to be the ultraviolet. Okay, so when they are jumping from this to all the way down here in the ground state, let's say directly, then in that situation what happens? It emits the ultraviolet. So the one that's jumping in the second first, that generates the visible colors. Okay, so there are these several chances. So they may come down here first and then they may jump here. So we have to look at all possibilities. Okay, so when they arrive all the way back there, they're going to emit UV. And remember, the largest gap is between, largest energy gap is between second and first. And once they go higher and higher, see, the energy gap becomes very small. And if they have enough energy to overcome all these values, right? Uh, if they get like, let's say, negative 13.6, slightly more than 13.6, it's going to get out from that. I should say positive 13.6. In that case, that electron's going to get out from the hydrogen atom. So it's going to get out from hydrogen atom means leaving the hydrogen atom without electron. And we say, okay, that is ionized hydrogen atom or hydrogen ion. That's what we say. Okay. So how do you produce hydrogen ion? So if you supply large enough energy for this electron, then what's going to happen? Some of these going to escape from the orbit. And that's how it becomes ion. Okay. So we can, if we don't know the numbers, for example, like here for this, we have numbers, but if numbers is not given, we can rewrite this equation using this. So, and this E1 being negative 13.6. Okay. And this equation is similar to, remember, this is HF HC over lambda. So now you can calculate the wavelength, and this equation is similar to that empirical equation first written by the Rydberg. Okay. So basically now Bohr has the explanation of all those spectrum, line spectrum. Okay. So now here is a question for you. So what do you think? So how many line spectrum are possible? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how we get. What do we get? So we have B, C, and E. Nobody chose D. Why no love for number 5? Okay, so let's draw all possibilities. This is basically, that is one photon that gives you one line spectrum. Another possibility is this. So that gives you another photon with a bit higher frequency or shorter wavelength. Okay. So that is another line possible. And another one is this one here. So there is another possible photon coming out. So this. Okay. But what happens is the one that arrived here eventually jumps down. So one possibility, it comes here. Let's go do this one first, all the way. So that emits photon. So that's another line. But it may come down from here to here first, and then come down here. Okay. And this one comes down here, but this is same as this one. So we don't need to double count because both of these produce the same line. Okay. So that means how many transitions are there? 1, 2, 3, 4, 5, 6. So it looks like E is correct answer in this case. We need to look at all possible combinations. Okay. So now let's actually plug in some numbers in the formula here. What is the wavelength when it jumps from the second excited state, second excited state to first excited state. Remember ground, we are saying ground is 1. So first excited state means n is equal to 2. Okay. And ground state has energy this much. And it also asks, is it in visible range? So yes, so we can first calculate the wavelength and then tell whether it is within the 400 to 700 or not. That's one way to do it. Another way, when it goes from n is equal to 3 to n is equal to 2, that was named as a Balmer series here, right? This Balmer series, these are the visible ones, okay? All of these are not visible. You cannot see, although those radiations are there. But so for example, this I said was ultraviolet, this is visible, and this I think is infrared, okay, and so on. And there may be, I don't know if that is radio waves, I forgot. I usually don't pay attention to that. But this is visible, okay? So now it's going to be in visible range. That's what we expect. Once we plug in numbers, see if we can get that value that matches with what we expect. So let's play with numbers here. So this is the formula, right? So delta E is E1 times 1 over n. Initial is n is equal to 3. So n3 square, and minus final is n is equal to 2. So that means it is n2 square. So this formula for this jump becomes this. Okay. Now we have number for all of these except over here. Let's say this can be written as h times f, and f can be written as, let's write in terms of wavelength, c over wavelength, and E1 is negative 13.6, and 1 over N3, so that means 1 over 9, 3 square is 9, right? Minus 1 over 2 square means 4. Okay, so we write that. So we have this pure number here. Over here, c, we know that is speed of light, and h, we know that is Planck's constant. So we need those numbers to find the wavelength. So here we are looking for wavelength is what? Wavelength of the photon emitted is what? Now, how do I proceed? Over here, I guess calculator would be good, but I think we can do this over here. So 4 minus 9 is negative 5. So that negative sign and that negative sign cancels, giving us positive number. So that means it becomes 13.6 times 5, divide that by 36. And by the way, this number is electron volt. That number is electron volt. So I guess I can still say, okay, that is electron volt, let's say, that is. So that means if I want to go to the joule, which is SI unit, I need to do this. 1 electron volt is 10 to the power negative 19 joule. Okay. So now, what is wavelength then? So what happens? We can do cross multiplication. Wavelength goes on the top, means these things come to the bottom of these, okay, take the place of wavelength. So I'm writing HC, and then this number here 13.6 times 5, and since this 36 is now becomes fraction of fraction over here, I can just write that one all the way there, and this 10 to the power negative 19 is gonna be in the bottom. Okay, so that's gonna be the wavelength. Let's see how far we can go. 36 times, now for H is 6.6 times 10 to the power negative 34, and C is speed of light, which is 3 times 10 to the power 8, and this is 10 to the power negative 18, so I can bring that up and write 10 to the power positive 19, and we have this 13.6 times 5. I think that's going to be 68. Okay. Now, this is 10 to the power 8. This is 10 to the power 19, means this is going to be 10 to the power 27 positive when we combine that. And then now there is negative 10 to the power negative 13, means that. Okay. So now, this is 10 to the power negative 7. So the exponents are 10 to the power negative 7. Now, how about the numbers? Let's see if we can get rid of some of these. So 4 times 9 is 36. 4 times 1 is 4, and 4 times 7 looks like that. So this became prime number, so I cannot cancel with the one on the top. So 27 point times 6.6 times 10 to the power negative 7. Divide that by 17. Okay. So now this is how much? We have few minutes. Let me pull my calculator here. And you also want to do independently so that we can check if the number matches. And by the way, it looks like I did not open chat today at all. My bad. So if you get number, let's say from your calculator, type that on the chat. And I'm also doing, I'll keep that 10 to the power negative 7. See, I like to handle exponents separately, as you may notice. So 27 times 6.6 is that much. Oh, that is nearly 10 times. Divide that by 17. So that is 10.5, let's say. Negative 7. And this being the wavelength, it has a unit meters now. Okay. So 10 to the power negative 7. So looks like for some reason I am not getting in the range. Let's see, what do we expect for the visible light? Yeah, looks like we are getting in the micrometer region. Okay. So yeah, 1.05 10 to the power negative 6 is same as just this one, okay? Because you can move that one, or you can go 105 times 10 to the power negative 8, or 1050 nanometer, okay? So this is kind of on the red side. So usually red up goes up to 700, I think. But let's see, what's the color of 1050 nanometer? Do you have your, let's say Google thing handy? So what's the color of 1050 nanometer light? Type that and see if it says some sort of red or not. Hopefully I did not make any mistake. This came out a little longer than what I expected. So I see infrared and red. Yeah, I guess close enough, right? Okay, then